For this homework or assignment, you are asked to do exercise 7.5a on page 203, problems 6 through 15. For this assignment, you are asked to prove whether or not these arguments are valid or invalid using the method of Venn diagrams. So we're going to begin by looking at problem number 6. And problem number 6, the argument you're given is the following. Some P are not M. And then you're given, I should write this out, 1, 2, and then some S are not M. And then finally the conclusion says some S are not P. Now, what you have to do is use Venn diagrams, and of course, in order to prove validity, we always diagram the two premises together in one diagram. So we begin by drawing our 3 circles in order to do just this. And we're going to begin, you're typically supposed to begin with the, let me label these S, M, and P, and then number our regions 1, 2, 3, 4, 5, 6, and 7. And you're supposed to typically begin with the universal premise because that makes it, or that provides a little more concrete information. And you don't, it's just like I've said before, it's just for practical reasons we typically begin with the universal premise, but we're not given a universal premise. And I'll tell you, heads up, I haven't even diagrammed this yet, and already I know this argument's invalid. You always have to have at least one universal premise. But we're going to begin with premise number 1. Some P are not M. And we need to come down here and look at the regions. P is 3, 4, 6, and 7. So we'll just write 3, 4, 6, and 7 right here. And M is 1, 2, 3, and 4. 1, 2, 3, and 4. And what we do, as always, is we find the regions of overlap, which in this case is going to be 3 and 4 here, and 3 and 4 here. And we scribble that out. And we're saying are not. So when you see are not, that means it is P is not in 3 and 4. So P must be in 6 and 7. And the way we show this is we put an X right there on the line between 6 and 7. That's how we show, because since it is not, P is not in 3 and 4, it's possible it could be in 6 and it's possible it could be in 7. And the way we show that possibility is by putting the X right there. Now we come to premise number 2. And what we do here is we say some S are not M. And we look at the region of S. And S is going to be 2, 3, 5, and 6. 2, 3, 5, and 6 right there. And then M is going to be, just as before, 1, 2, 3, 4. And here again, we circle the regions of overlap, which is going to be 2 and 3 here, and 2 and 3 here. And we can scribble out the 4 and scribble out the 1. We don't need those. And we're saying some S are not in 2 and 3. So if they're not in 2 and 3, that means the only possibility left is 5 and 6. So the way we show that is we put an X right there on the line. Now what we do is we're going to come to diagram the conclusion. And in order to do that, we draw up our 3 circles just as before. I'm going to move this a little down here so I have some room to work with. And then we're going to do S, P, M. Still don't have enough room to work with, but that's all right. So region number S, we're going to just work with here is 2, 3, 5, and 6. And P is going to be 3, 4, 6, and 7. All right, and so what we do, as always, is we circle the region of overlap, which is 3 and 6, and 3 and 6. We can scribble out the 4 and scribble out the 7. And we're saying, oh, I forgot to number these. 1, 2, 3, 4, 5, 6, 7. It's not allowing me, for whatever reason, to write a 6 in the 6 hole. So I don't know what the reason is here. There we go, 6. So what we are saying is that some S are not in 3 and 6, so that means it can only be in 2 and 5, so we put an X right there on that line. Now, in order for this argument to be valid, the premises over here, they have to definitively put an X either in region 2 or in region 5, because it's only in those two regions that this conclusion would absolutely be true. If there's an X either in 2 or in 5, then 3 would be guaranteed, and it would be true. It would be guaranteed by the premises. Now the question is, does this diagram over here definitively put an X in 2? No, it's nowhere near 2. It doesn't have an X at all in 2. Does it definitively put an X in 5? And the answer is no. And so for that reason, this argument is invalid. Man, that is poorly written. But it's invalid. So argument 6, invalid. All right. Well, let's clear all. Maybe I'll write a little neater this time. I'll try. I keep saying that. It hasn't worked out so far. Number 7. So here's the argument we're given for number 7. It says some MRP, all MRS, therefore some SRP. Now, what is the, we could do this. I probably should have done this on the previous one. But what is the mood of this argument? Hopefully you said it's I, and the figure is figure what? Anybody want to take a guess what the figure is? The figure in this one is figure 3. So anyway, well, let's begin by diagramming the combined premises. So that's where we start. We're going to diagram the combined premises here. Get our circles. So S, M, P, and let's number our regions. 1, 2, 3, 4, 5, 6, 7. I know it's a little tedious me drawing this out every single time, but I think just the more you see me drawing the diagram, the more it's going to sink in. So we have two premises here, 1 and 2, and which one should we diagram first? Well, we should diagram the second premise first because it has a universal quantifier, whereas the first one has a particular quantifier. So let's begin by diagramming that first. All M are S. And M is going to be regions 1, 2, 3, and 4. 1, 2, 3, and 4. And S is 2, 3, 5, and 6. 2, 3, 5, and 6. Okay, and what we do is we circle the regions of overlap. 2 and 3, 2 and 3. Scribble out the 5 and 6, we don't care. Now what this is telling us is that all the M's are located in 2 and 3. And what do we do when we are diagramming a proposition that has a universal quantifier? Whenever we have a universal quantifier, we know we're going to use shade. We always use shade. But what does shade mean? Shade means empty. Shade means nothing. Shade is negative. You know, when you throw shade at someone, it's negative. So we can't show that things are positively represented in 2 and 3 with something negative. So we're going to have to say use shade in order to show that something's in 2 or 3. And the way we do that is we're going to shade in 1 and 4. That's how we do this, because we're saying not in 1 and 4, therefore it must be in 2 and 3. All right, so we got that out of the way. Now we come to premise number 1. We're going to do number 1 now. And this says sum M R P. And region M is 1, 2, 3, 4. And P is 3, 4, 6, and 7. So what we're going to do is we're going to circle the regions of overlap, 3 and 4, scribble out 6 and 7. And this is saying some are in 3 and 4. Well, we can't put an X in 4 because we already know that it's empty. So we put an X in 3. It's the only place left because it's R, M, R in 3 and 4. All right, now finally we come to the conclusion. And let me see if I can't get my circles here. Just as before, we're going to do S, P, M, 1, 2, 3, 4, 5, 6, and 7. All right, and for this one, we're saying sum S sum S R P. So S is regions 2, 3, 5, and 6. 2, 3, 5, and 6. And P is 3, 4, 6, and 7. 3, 4, 6, and 7. And what we do here is we circle the regions of overlap, which is going to be 3 and 6. It's going to be 3 and 6. We scribble out 4 and 7. We don't care. And what we are saying here is that some S are P, and they could be, and the S could be in 3 or 6. And the way we show that possibility is we put an X here. Now, this statement is true. The conclusion, when I say this statement, I'm referring to this conclusion, is true and is guaranteed by the premises just in case the combined premises, if the combined premises locate an X definitively either in 3 or in 6, then this argument is valid. And we look over here and we see that the combined premises definitively put an X in 3. And since they definitively put an X in 3, this argument is indeed valid. So, like I said, the way to prove validity is once we diagram the premises, it's true, or I say it's true, I mean the conclusion is true. The conclusion is guaranteed to be true by the premises just in case the combined premises put an X definitively either in 3 or in 6, and they do that. You know, another way you can do that, determine this is valid, is just look at what this conclusion is saying. It's saying some S or P, and look where that X is. It's in S and it's in P, so it's definitively saying some S or P. I mean, you can kind of just look at these a lot of times and just tell, but all right, so moving right along to number 8. Sorry, I don't know if any of you care, but I hurt my right hand. I have a pinched nerve in it right now, and I'm having a difficult time writing, even more so than normally. So I'm having to write a lot of this stuff left-handed. I have to go back and forth between my hands. So when my handwriting is exceptionally bad, I'm going to blame it on using my left hand. So you'll be able to tell, I think. Well, maybe not. I don't know. My handwriting's pretty atrocious in general. So, all right. All S, R, M. some S are not P. All right. So this is the argument we're given for number 8, and we're going to draw our Venn diagram here. And let's see, get our S, our M, and our P. And then we're going to number our regions. 1, 2, 3, 4, 5, 6, and 7. And that might be the world's worst 7. I don't know. That one's not a lot better. So we have to diagram the combined premises. And like I've said many times, you begin with the premise that has a universal quantifier. So we're going to begin with all S are M. So let's write it over here just so we can, all S are M. And S, let's see, contains 2, 3, 5, and 6. 2, 3, 5, and 6. Whereas M is 1, 2, 1, 2, 3, and 4. Okay, so what we do is we're going to circle the regions of overlap, which is 2 and 3 here, 2 and 3 here, and we scribble out those. And we're saying all are in 2 and 3. Well, if they're all in 2 or 3, remember we're using shade because we have a universal quantifier. If you see all or no, you're going to use shade. And we're saying all the S are located in 2 and 3. So if we're going to say they're all in 2 or 3, we're going to shade in 5 and we're going to shade in 6. Because remember, shade is negative. Just like when you throw shade at someone, it's negative. And I wouldn't say something is in 2 or 3 by saying something negative. I'm going to basically, you know, when you're throwing shade here, you're putting it in the region to show where stuff isn't. So if we haven't made that abundantly clear. All right, so now we got that out of the way. We're going to come to our first premise. Some M are P. And M is 1, 2, 3, and 4, whereas P is 3, 4, 6, and 7. So we locate the regions of overlap, 3 and 4, 3 and 4, and we can scribble out the 6 and the 7. And we're saying some M are in P. So some M are in 3 or 4. Well, we can't put an X, since we see some, we know we're using an X, and we can't put it in, I'm sorry, actually we can. I was looking at the wrong number. We could put the X in 4 or in 3. And the way we show this option here, this possibility, is by putting an X right there at the overlap. So that's how we would diagram the combined premises. Now, we diagram the conclusion. And in order to diagram the conclusion, just like before, get our 3 circles, and we're going to S, P, and M. 1, 2, 3, 4, 5, 6, 7. And we are going to come over here. This is where it can work. Some S are, oh goodness, maybe it can't work there. I'll just work under here. This will be fine. So S is region 2, 3, 5, and 6. 2, 3, 5, and 6. And P is 3, 4, 6, and 7. So we locate the regions of overlap, which is going to be 3 and 6, 3 and 6. We don't need 7. We don't need 4. And we're saying, notice here, are not. Are not. So it is are not in 3 and 6. And if it's not in 3 and 6, it must be in 2 and 5. So to show that it could be in 2 or 5, we put an X there. Now, in order for this argument to be valid, the combined premises, this diagram right here, must definitively put an X, either in 2 or definitively put an X in 5. Does it do that? The answer is no. And so this argument is invalid. All right. That was number 8. On to number 9. And number 9, you're given this argument. Some P are not M. Just had an epiphany. Maybe this will work. All, maybe I'll leave a little space right here. I don't have to rewrite the premises. All S are M, and then therefore some S are not P. Some S are not P. And then what we're going to do is we're going to, just as before, draw our trusty Venn diagrams. Stop that. I want to move this a little bit here. I think that'll work. All right, and so we're going to S, P, and M. 1, 2, 3, 4, 5, 6, 7. My regions aren't exactly proportional here, but it really doesn't matter. So we're going to begin by diagramming the combined premises, and we begin with the universal premise because that tells us the most definitive information. And again, since we have a universal quantifier, all or no, we use shade. And so region S is 2, 3, 5, and 6. Region M is 1, 2, 3, and 4. So we circle the regions of overlap, 2 and 3, 2 and 3, scribble out the 4, scribble out the 1. And we're saying all S are in M. And this is actually just like the previous one. If they're all in 2 and 3, that means there's nothing in 5. That means there's nothing in 6. So we use a shade to indicate that. Now we come up to the top. Some P are not M. So P is going to be 3, 4, 6, and 7. M, 1, 2, 3, and 4. And we circle the regions of overlap, which in this case is 3 and 4. 3 and 4. We scribble out that. And we're saying are not. Make sure to pay attention to that. So it's are not in 3 and 4, which means it is in 6 or 7. But notice 6 has already been scribbled out. So this is the only place we can put an X. Then we come over here and we're going to diagram our conclusion. And just as before, S, P, and M. 1, 2, 3, 4, 5, 6, 7. Again, I didn't do a good job of making those regions proportional. Doesn't really matter. Region S, 2, 3, 5, and 6. 2, 3, 5, and 6. Region P is 3, 4, 6, and 7. And we circle the regions of overlap, which every case, you notice it's always 3 and 6 in the conclusion. And we're saying are not. Pay careful attention to that. So it's are not in 3 and 6, which means what? If it's are not in 3 and 6, it can only be in 2 and 5. And how do we show that? By putting an X right there. And so when we look at this argument, in order for the conclusion to be valid, or in order for the argument to be valid, the combined premises must place an X, either definitively either in 2 or 5. And they don't do that. And for this reason, this argument is invalid. This is not a valid argument here. Wow, looking at that screen, that's just a jumbled mess, isn't it? I don't think that method worked as well. So, but that argument was invalid. Number 10. All M are P, all S are M, therefore all S are P. Anybody know the mood of this? It's AAA, and the figure is 1. AAA 1, I believe, from memory, is a valid argument, but we're going to prove it. And we're going to prove it using, you guessed it, our beloved Venn diagrams. So S, P, M, 1, 2, 3, 4, 5, 6, 7. Yeah, I bet you guys didn't know it was going to be this much fun when you signed up, did you? You had no earthly idea. Well, we can begin. We're going to begin by diagramming the combined premises, and we can pick either one since both use a universal quantifier. We'll just start with the first one. All M are P, and M is 1, 2, 3, and 4. P is 3, 4, 6, and 7. They overlap. We circle that. And we're saying all are in 3 and 4. And we're using shade. And in order to show that everything's in 3 or 4, we're going to shade in 2 and shade in 1 because we're saying nothing is in that region. All right. Now we come to premise number 2. All S are M. And S is region 2, 3, 5, and 6, whereas M is 1, 2, 3, and 4. We circle the regions of overlap, which is 2 and 3, 2 and 3. We color that out, shade, get rid of that. We don't need that. We're saying all is in 2 and 3, which means none is where? That's right, nothing in 5 and nothing in 6. Now finally, we come to the conclusion, which is all S are P. And we need to draw up our trusty Venn diagram of the conclusion. And just as before, S, P, M, 1, 2, 3, 4, 5, 6, 7. And S is region 2, 3, 5, and 6. P, it is going to be 3, 4, 6, and 7. And just like always, it's going to be 3 and 6, 3 and 6. And we're saying all are in 3 and 6, which means none are where? Nothing in 2 and nothing in 5. Now, when we're dealing with an argument that has a universal conclusion, notice that we have to, whatever we shade in the diagram of the conclusion, as right here, whatever regions we shade in must be shaded in over here. So here we shaded in region 2 and region 5. Are those regions shaded in over here? Yes, it's shaded in 2, and yes, it's shaded in 5. And for that reason, this argument is indeed valid. Now we can always shade in more in the combined diagram, but we can never shade in less. So this argument is indeed valid. All right. We're on to number 11. Okay, so let's do 11. No, P is M, some, whoa, what just happened there? Some M are S, therefore some S are not P. Okay, now let's draw our circles just as before. S, P. You guys hopefully are getting quite familiar with this now. All right, so with this one, we're going to begin by diagramming, like always, the combined premises. And we need to start with the one that has the universal quantifier right here. So we're going to start with the first one. No P is M, and P is 3, 4, 6, and 7, while M is 1, 2, 3, and 4. We circle the regions of overlap. 3 and 4, 3 and 4. We scribbled that out. And we're saying no. We're saying no P is in 3 and 4. And how do we show that no P is in 3 and 4? Well, in this case, we shade in 3 and we shade in 4. And that lets us know that nothing is in 3 and 4. All right, now we come to premise number 2. Sum M R S. Just out of curiosity, what is the mood of this? It is E I O, and it is figure 4. So hopefully you got that. M is 1, 2, 3, 4, and S is 2, 3, 5, 6. And we circle the regions of overlap, which is going to be 2 and 3, and 2 and 3. We scribbled that out. And we're saying R. So we're saying it is R in 2 and 3. Now, here, what we have to realize is that since we're saying it is in 2 and 3, we can only place an X in 2 and 3. By shading in the universal premise first, though, we know that 3 is off limits. 3 is empty. There's nothing in 3. So the only place we can put an X is right there in region 2. And now we come to the diagram of the conclusion. S, P, M, 1, 2, 3, 4, 5, 6, 7. And let's see, some S are not P. Some S are not P. S is 2, 3, 5, and 6. And P is 3, 4, 6, and 7. Circle the regions of overlap, 3 and 6, 3 and 6. Scribble out this, and we're saying are not. So it's are not in 3 and 6. So that means that if it's not in 3 and 6, we have to put it right here. And this argument, since we're dealing with a particular conclusion, it is valid just in case the combined premises, the diagram of the combined premises, if it definitively puts an X either in 2 or definitively puts an X in 5. Does it do that? Does it definitively put an X in region 2? Yes, it does. And so for that reason, this argument is valid. Number 11 is definitely a valid argument. All right, in the home stretch now, people. Number 12. All right, all PRM, sum MRS, and then sum SRP. All right, let's draw our circles here. Our happy little circles. I'm gonna go all Bob Ross on you. If you guys don't know who that is, you should look him up on YouTube. All right, just happy little circles. All right, so we're going to begin diagramming the combined premises, and we start with the premise that has the universal quantifier. All P, I'm not going to write out the whole thing again. I'm just going to write the numbers. So P is 3, 4, 6, and 7. And M is 1, 2, 3, and 4. So we circle the regions of overlap. We scribble this one out. And we're saying all are in 3 and 4. Well, if they're all in 3 and 4, that means where are they not? They're not in 6. They're not in 7. So hopefully you see I wrote the numbers out to correspond with the P, and these numbers right here correspond with the M. It's a little, at this point, hopefully you're getting that. Now we come to this. All M is 1, 2, 3, and 4, are S, which is 2, 3, 5, and 6. 2, 3, 5, and 6. Circle the regions of overlap. 2 and 3, 2 and 3. Scribble that out. And we're saying that R, I'm sorry, I lost my train of thought. M is in 2 and 3. So the way we show that it is in 2 and 3 is we put an X right there on 2 and 3. Now we come to the conclusion. We're going to diagram the conclusion, and we have to come up with a separate diagram for it. Okay, so we're going to do a separate diagram for the conclusion. And sum S is 2, 3, 5, and 6, are P. And P is 3, 4, 6, and 7. We circle the regions of overlap. 3 and 6, saying R. So at R in 3 and at R in 6. Now, this argument is valid if the combined premises, if they definitively put an X either in 3 or 6. Does it definitively put an X in 3? No, because that is on the line between 2 and 3. Does it definitively put an X in 6? No, it actually rules 6 out. There's nothing there. And so this argument is invalid. All right. So number 13. No M is P. Some S are M. And then some S are not P. Okay. S, P, M, 1, 2, 3, 4, 5, 6, 7. So we're going to begin with diagramming the combined premises, and we'll start with the one that has the universal quantifier. M is 1, 2, 3, 4. Doing M. Then we're going to come and do P. P is 3, 4, 6, and 7. Circle the regions of overlap right here. Scribble this out. And we're saying no to 3 and 4. So we just shade in 3 and 4 because we're saying no to 3 and 4. Now we're going to come and we're going to diagram second premise. Sum S is 2, 3, 5, and 6. 2, 3, 5, and 6 are M. 1, 2, 3, and 4. So we're going to circle the regions of overlap, 2 and 3, 2 and 3, scribble that out. And we're saying R in 2 and 3. Well, 3 has been excluded, so we're going to just put an X in 2 because we've excluded this one, region 3 that is. Now we're going to come and we're going to diagram the conclusion. S, P, M, 1, 2, 3, 4, 5, 6, 6. Low battery. Hopefully we'll get done. Okay, so sum S. S is 2, 3, 5, 6. P is 3, 4, 6, 7. 3, 4, 6, 7. Circle the regions of overlap. Scribble that out. And the key word here, not. So we're going to put an X. We're going to say are not in 3 and 6. Well, if there are not in 3 or 6, where are they? It's going to be right here on this line. And so this argument is valid just in case the combined premises, if they definitively put an X either in 2 or in 5. And when you look over here, and lo and behold, it does definitively put an X in 2. And for that reason, this argument is valid. And you can also just look at it, because the conclusion says some S are not P, and we're putting an X right here. And that just says some S, that just tells us some S are right here, which is not in the region of P. So I think for the last couple, I'm going to get a little crazy and not draw up my diagram in full. What do you guys think? I think that's just crazy enough it might work. All right, so on to number 14. All P are M, no S is M, and then finally no S is P. And we're going to begin by diagramming the combined premises. Since both of them have a universal quantifier, we could diagram either one first. Doesn't matter. So we'll just start with the first one. Why not? And it's saying all P, which is 3, 4, 6, and 7, are M, which is 1, 2, 3, and 4. We circle the regions of overlap. All right, we scribble this one out. We don't matter. And we're saying all of it is in 3 and 4. And if all of it is in 3 and 4, that means none is in 7 and none is in 6. None is in 6 or 7. That's how we show this relationship right here, or this premise right here. All right, now we come to the second one, and we're saying no S, which is 2, 3, 5, and 6, is M. 1, 2, 3, 4. We circle the regions of overlap. 2 and 3. 2 and 3, we scribble out the 4, we scribble out the 1, and we're saying, this time we're saying no to 2 and 3. So what we're going to do is we're saying no to 2, we're saying no to 3. Finally, we come to the conclusion. And with the conclusion, we're saying no S, which is 2, 3, 5, and 6, is P, 3, 4, 6, and 7. 3, 4, 6, and 7. And what we do is we circle the regions of overlap, which is 3 and 6, 3 and 6. And we're saying no to 3 and 6. So we say no to 3, we say no to 6. Now this argument is valid just in case the combined premises, if they shade in the same regions that the conclusion does. The conclusion, or let me rephrase it, at least the same regions. So the conclusion shades in 3. Well, over here we shaded in 3, right? Right here we shaded in 3. Conclusion shaded in 6. Over here we shaded in 6. And for that reason, this argument is valid. And this argument, wait a second. Oh, sorry, I lost my train of thought here. The mood of this argument is AEE. And the figure is figure 2. Okay, so last one. I know you guys are happy as can be. So we don't have to do any more of these today. 1, 2, 3, 4, 6, 7. 1, 2, 3, 6. All right. Number 15. All M are P, Some M R S, some S R P. And the mood of this argument is A, I, and the figure is figure 3. So let's begin. We're going to begin by diagramming the combined premises, and keep in mind we always start with the premise that has the universal quantifier. So all M is 1, 2, 3, 4, and P is 3, 4, 6, 7. We circle the regions of overlap. We scribble that out. All are in 3 and 4. Well, if they're all in 3 and 4, that means they're not where? Nothing in 1 and nothing in 2. So we shade those in. All right. Now we come to premise number 2. Some M, 1, 2, 3, and 4, are S, which is 2, 3, 5, 6. Circle the regions of overlap, which is 2 and 2, and 3 and 3. And we're saying that they are. So they are in 2 and 3. Well, look, we've shaded in 2, so we can't put anything there. So we're going to put an X right here in 3. Then finally we come to the conclusion. Some S R P. Now you can just look at it and tell that this is valid, but we're going to do it anyway. So some S is 2, 3, 5, and 6, and P is 3, 4, 6, and 7. We circle the regions of overlap, which is going to be 3 and 6, and 3 and 6. Shade that in, and we put an X right there on the line. And the argument is valid just in case if the combined premises definitively put an X either in 3 or in 6, it's going to be valid. Now let's look over here. Do they definitively put an X in 3? Yes. It doesn't matter about 6 since they already did it for 3, but it definitively puts an X in 3, and so this argument is valid. I mean, if it had been the case that it definitively put an X in 6, it would also be valid. When I said it didn't matter about 6 because we already had an answer to whether or not it definitively put an X in 3. And that's sufficient. If it definitively puts an X in either 3 or 6, the argument turns out to be valid. So hopefully you're getting a better sense of how all of this works. And I hope some of this is starting to make sense. I know it's a little bit repetitive and there were a lot of exercises, but with this, as with all skills, just the more you practice and repeat and repeat and repeat, the better you're going to get at it.